All right, so you want something like the antiderivative of, I heard you say x to the fifth plus x squared minus 3, maybe, over x plus 1. What in that problem tells you you should use long division?
The power on the top is greater than the power on the bottom.
Perfect. When the power on top is greater than the power on bottom, or if they were equal, that's a good indication you should do long division. All right, so long division here is kind of a pain in the neck, because what we have to do is we have to do x to the fifth, and then I need to fill in a plus 0x to the fourth, because there isn't an x to the fourth. I need a plus 0x cubed, because there was no x cubed term, plus x squared, and then I need a plus 0x minus 3. So you have to fill in all of the missing terms. So we were missing x to the fourth, x cubed, and x. So we had to fill them all in with zeros.
Can we make it over x squared plus 1 to make it a little bit more complex division?
You can put it over x squared plus 1, but then we can't answer it.
Oh, okay, we can't do long division then?
No, you would do long division, but what you would end up with eventually, you would end up having to do an integral of a constant divided by x squared plus 1, and we don't know how to do that yet. We will learn soon. That's a trigonometric substitution problem. Okay? All right. If we had x squared plus 1, if it was x squared plus 1, then again we would have to write x squared plus 0x plus 1. You'd have to fill in there too. X plus 1. All right, so this problem is 90% algebra, because most of the work is going to be to do this division. That's x to the fourth. So you have x to the fifth plus x to the fourth. And you subtract, you get negative 1 x to the fourth plus 0x cubed. Then I need a negative x cubed. Negative 1 x to the fourth minus x cubed. Subtract, I get a positive x cubed plus x squared. And then I have a plus x squared. So that's going to give me x cubed plus x squared. And something a little unusual happens. They both cancel out, don't they? So since they both cancel out, what do I need to do? I would have a 0. I would need to bring down the 0x, but that's not really going to help, and I need to bring down the 3. So I think I've actually done the division at this point, because the only thing I have left down here is minus 3. Can I turn an x into a minus 3? No. All right, so there's my remainder. So I think this becomes the integral of x to the fourth minus x cubed plus x squared minus 3 over x plus 1. So that was some nice random luck there, because I just kind of picked these polynomials at random, and it just so happened that I didn't have to do a bunch of the division. It all canceled out. Sometimes you get lucky that way. dx. Final answer is 1/5 x to the fifth minus 1/4 x to the fourth plus 1/3 x cubed minus minus 3 ln of absolute value of x plus 1. Very good. Plus c. Questions on that one?
So I guess, did you skip the u substitution part?
Yes.
Okay.
Yes, I did. Very good. This last part right here really requires a u substitution. But it's a very nice u substitution. I would have the antiderivative of minus 3 over x plus 1 dx. And this is a really nice one, because u would be x plus 1, and then this works out perfectly. Du would be exactly dx. So I don't have to worry about fixing any little number issues. This one works out perfectly. So I did skip that because somebody told me the answer. I just skipped right over it. So that turns out to be minus 3 over u du, which is 3 ln u negative 3 ln u. And then you plug your x's back in. You plug in your x plus 1. Yes?
So if that was a 2 dx, would you have to multiply that with -3?
Correct. So if this were a 2x here, then when I took the derivative, I would get a 2 dx, which means I'd have to put a 2 in here, and I'd have to put a 1/2 out there. So I'd actually end up with a negative 3/2 altogether. Yep.
Now, does it matter what the sign is on the top when you plug it, when you convert it to ln? Like if it's negative or positive?
Nope. You mean this negative 3, does it matter?
Yeah, like, yeah, over to the left, and it's negative 3 divided by u. If it was just 3, would it be ln still?
Yep, it would still be 3 ln u if this were a positive 3 instead of a negative 3.
It would be plus the.
But it would be plus 3 ln u at the end there, yeah. Yep. Other questions? All right, here are some other problems you're going to see in section 5.2. You're going to see some problems that look like this. The antiderivative of 1 over 1 plus square root of 3x dx. And on this problem, they tell you to use u substitution. And they even very specifically say, let u be the bottom. So u is the bottom, right? Kind of a dumb statement there. U equals 1 plus the square root of 3x. Oops. Dx. Take the derivative. du is, what's the derivative of 1 plus the square root of 3x? 1/2. 3x to the negative 1/2 times 3 dx. So I kind of have a problem here. The problem is, here's my u. That's not the problem. The problem is, I got dx and dx, but I have all that other junk there that I somehow need to deal with. What do I do with all that junk? Somehow I'm going to have to change it and make it be
1. Well,
or at least u's, correct? Because when I do my u substitution, everything inside here has to be u's.
So you divide it?
Divide it? So are you saying get dx all by itself?
Yeah.
Yeah, that's a great idea. So to get dx all by itself, I have to multiply by 2 and divide by 3. So that's going to be a 2/3, right? So that's 2/3. And then how am I going to get rid of this 3x to the negative 1/2? Let's leave it there for a minute. Du. All right, so all I did in one step there is I got rid of the 2/3. I got rid of the 3/2 by multiplying both sides by 2/3. I want to get this over to the other side. What do I do with that? I could divide it on both sides. So how do I take and divide by 3x to the negative 1/2? What does a negative power do? Puts it on bottom. So what I'd prefer to do is I'd prefer to think of this negative 1/2 puts this thing on bottom. So how do I get rid of something that's on bottom already? Multiply it. So I'm going to take this equation here, and I'm going to multiply everything by 3x to the 1/2. And that'll get rid of that 3x to the negative 1/2. All right, so that gives me 2/3. 3x to the 1/2 du equals dx. Okay, so we're almost ready to make our u substitution. Again, back up here, this is our u. Dx is 2/3 3x to the 1/2 du, but the problem is when I make my substitution, I'll put an x back in there, and I'm not allowed to do that. So I somehow need to get rid of this little piece here and turn it into u's. It's the same sort of back substitution problem that we've done before. Exactly right. Square root of 3x is u minus 1, isn't it? And isn't this just another symbol for square root of 3x? Yeah, because a 1/2 power is a square root. So the square root of 3x is u minus 1. The square root of 3x is u minus 1. So this becomes 2/3 times u minus 1 du equals dx. So it's that same sort of trick that we used in Calc 1 before, where you would let u be 1 plus 2x maybe, and then you had to get the x all by itself and plug that in also. Same sort of deal. Just a little bit different because here we're plugging into the du and the dx area. It's a little different, but same sort of idea. Okay, so this becomes, we're almost set to go here. This is the integral. I'm going to have a 2/3. I'm going to have a u minus 1, and then I'm going to have a u on bottom from that thing, and then a du. So there's my u substitution. Now what? Do what?
Distribute and cancel.
Yeah, I'm hearing the right things. Again, what I notice is my power on top is the same as my power on bottom. So I'm just going to divide. Or I heard somebody say distribute. You could think of this as being u to the negative 1. Distribute it through. Exactly. 2/3 was u divided by u. Yeah, that wasn't a trick question. That's 1 minus 1 over u du. And now we have something we can integrate. That's 2/3 times u minus, what's the antiderivative of 1 over u? That's ln, absolute value of u, plus c. And my last step, of course, is to plug my x's back in. So my final answer looks like 2/3 times 1 plus square root of 3x minus ln of 1 plus square root of 3x plus c. Questions on that one? Go ahead. Actually, I don't think we actually need the absolute value symbols. Well, x can't be a negative, can it? Because I can't take square root of a negative number. You would get imaginary, and we don't deal with imaginary in Calc 1 or Calc 2. Okay? So I do believe in this case the absolute value symbols are optional. You don't need them. Not wrong to have them, but you don't need them. That thing is always positive. Other questions?
So, ln u derived, that's the u1 divided by u, right?
Yes.
Okay. And when you integrate it, you get the just like function.
Right. And the reason is, when we defined absolute value, I'm sorry, not when we defined absolute value. When we defined natural log, the way we defined natural log was the integral from 1 over x to 1 over t dt. And we specifically said x had to be bigger than 0. And the problem was if x were a negative number, then we had a discontinuity in this function 1 over t. And once we had the discontinuity, the integral was no longer defined. So when you take the derivative, according to the second fundamental theorem of calculus, you just get 1 over x. But again, our restriction here is x can only be a positive number. But then when we go to do antiderivatives, remember antiderivative means area, correct? And so the graph of y equals 1 over x looks like this. So it would be possible to talk about that area right there. So it is possible to talk about x being negative values. Of course, you can't see that area, which makes it harder for you to understand. There you go. We could have x going from -3 to -1 and have the area under the integral. So we could talk about the antiderivative from -3 to -1 of 1 over x dx, and that would be ln x -3 to -1. And without the absolute values, we'd have a problem. Because without the absolute values, can I plug in -1 and -3? No. And so that's why when we do antiderivatives, that absolute value comes in so that that area does actually make sense. Okay? You're welcome. Other questions?
You have a fraction, you put ln on top and bottom. You don't have to do it. It's balanced, right? As long as the ln's on top and down, right?
Not sure what you mean by as long as the ln's on top and bottom.
Like if I had 2/3, and I was like, well, I want to put ln, since ln 2 divided by ln 3, that's the same as 2/3 still, right?
Nope. If you have ln of 2/3 is not the same as ln 2 over ln 3. Our rule was if I have ln of 2/3, ln's take division and turn them into
Well, I
subtraction.
mean, like if you initially had 2/3,
Uh-huh.
could you just set, you can't just put an ln.
No. Just like you can't take 2/3 and just square it. It's not the same, right? If I were to take 2/3 and square it, I get 4/9, so it's not 2/3 anymore. Yeah, if you do an ln of a number, it changes the value.
What would be like the best way to, is there a way to put an ln there, like if you wanted to, like if there was an equation on top and bottom? Like how would you?
Well, if you haven't, so you're confusing things. You're saying you have an equation on top and bottom. Equations don't go top and bottom. If you had an equation, 5x equals 7, then you can do ln on both sides. You can do ln on both sides of an equation. I'm not sure why you would want to on this equation. It certainly wouldn't help anything, but you could.
Okay. Yeah.
If you have a fraction, if you had 2/3 x equals 5, and you did ln on both sides, then the whole 2/3 would have to go in the ln. You can't split the 2/3 up nicely.
Okay. Yeah,
Okay.
what I'm saying, yeah, is like, would I have to do the 5 for those strips?
Absolutely, you would have to do the 5. But what would we typically do with that 5? We would typically say logarithms take multiplication and do what to it? Turn it into addition. So this left-hand side, we would typically write that way. Okay?
And that's equivalent, the 5x equals 7 is equivalent to ln 5x equals ln 7?
Yes.
Okay. Because you're just doing it to both sides of the equation.
Right.
Like multiplying by 1 on both sides.
Or multiplying by any number, right? If I have an equation, if I have 5x equals 7, I can multiply both sides by 3.
Okay, but you would never divide, like, multiply one side of the equation by ln as though, if sometimes you want to get, multiply the top and bottom of a fraction by 2 or x or something like that. We can't do that with ln.
You could, as long as it's the same ln. Again, I'm not sure why you would want to, but if you had 5/8, you could multiply top and bottom by ln2, because ln2 divided by ln2 is just a fancy way of writing the number 1. I'm not sure why you would want to do that, but you could. Makes it uglier as far as I'm concerned, but you could do it. When do you want to do ln on an equation? When is that a good thing to do?
You want to bring something that has a derivative of
true. We did see that using ln's on both sides could eliminate having to use the product rule, quotient rule. I was thinking more something along these lines. If I was trying to solve an equation, ln would get rid of e. So if you want to solve an exponential equation, this is where you use ln's typically.
Can we solve that then?
Absolutely. How would you solve that?
Multiply by ln.
You could do ln first. Typically, what I would do is I would divide by the 5 first. And then we would apply ln on both sides. It's not really a multiply because ln's not a number, it's a function. And then the important thing is, what do ln and e to a power do to each other? They reduce each other. They're opposite, they're inverse functions. So ln of e to the 6 is, or e to the 6x is 6x. So we would have 6x is ln 9/5. Divide x is ln of 9/5, all divided by 6. So that's the kind of problem where you would use ln on both sides. Use ln to get rid of e's. Other questions? All right, the other thing that shows up in this section is we have some new rules. You might remember from Calc 1, we had some trig rules. For example, we had a rule for the antiderivative of sine x dx. What's the antiderivative of sine? Negative cosine or cosine?
Oh, it's negative cosine. Because cosine is negative sine. So it's negative cosine.
What's the derivative of sine?
Cosine.
The derivative of sine is positive cosine, so the antiderivative of sine is negative cosine. You have to keep your minus sign straight there. What's the antiderivative of cosine x? Sine x. And then we had some kind of strange ones. What I mean by that is we had a formula for the antiderivative cant squared. Nope. Oh, we did have a formula. Are you saying we have a formula for antiderivative of secant tangent? Because we do have one of those too. The antiderivative of secant squared is tangent. That's exactly correct, because the derivative of tangent is secant squared. So in Calc 1, that always struck me as kind of weird, that we had a formula for the antiderivative of secant squared, but we didn't have a formula for secant. That's correct. And we also had a formula for secant tangent. The antiderivative of secant tangent is secant. Yet we didn't have a formula for secant all alone, and we didn't have a formula for tangent all alone. But yet you put them together, and we had a formula. Kind of weird. Well, here's the good news. We're going to fix all that. All right. So here, and similarly, we had a formula for the antiderivative of cosecant squared. The antiderivative of cosecant squared was negative cotangent. And the antiderivative of cosecant cotangent was negative cosecant. Yeah, those had the minus signs on them. All right. What about, here's a new one, the antiderivative of tangent. What I'm going to do is I'm going to take tangent and I'm going to write it as a fraction. Tangent is, of course, sine over cosine. Then what? What's that? There's an integral for sine, I agree. And there's an integral for cosine. But we do need to use u substitution. I can't just do the integral of sine divided by the integral of cosine, can I? We don't have a quotient rule like that. But we do have a fraction. And when we have fractions, the general idea is use u substitution. What's u? U should be cosine. And usually when you have a fraction, u is the bottom. So we're going to let u equal cosine x, which means du is negative sine x dx. Notice how nicely that works out. Because I have a sine x dx up on top, I really need a negative sine x dx, so what do? Just negate it. So this is going to be negative integral 1 over u du. And then we have a nice formula. What's the antiderivative of 1 over u? Negative natural log absolute value of u plus c. So that's negative natural log absolute value of cosine x plus c. So now we have a formula for the antiderivative of tangent. And that's why we didn't have it in Calc 1, because in Calc 1 we didn't have any ln's. You will also sometimes see this written this way. In fact, this is probably the more common way. ln absolute value of secant x plus c. How are those the same? Secant is 1 over cosine, correct? So how did cosine turn into secant and my minus sign disappeared? That's one of the rules of logarithms. Logarithms take things out front and turn them into powers. So if I take this minus sign inside, that becomes cosine to the negative 1 power, which is 1 over cosine, and 1 over cosine is secant. All right, exact same trick with cotangent. Integral of cotangent x is the integral of cosine x over sine x. But that one's even nicer, because if u is cosine, then u is the bottom. If u is sine, the derivative of sine is cosine. I don't have that little negative sign problem, little negative issue this time, do I? U is sine x, du is cosine x dx. So that becomes the integral of 1 over u du. That's ln of u plus c. So the antiderivative of cotangent is the natural log of the absolute value of the sine. Questions on those? All right. The antiderivative of secant x. This one's a little bit trickier. Here's what we're going to do for secant x. It's not obvious that this is the right signing. Tangent and cotangent, it was pretty obvious, right? M as fractions, use substitution. This one's not so obvious. What you do with this one is you rewrite this. I'm going to rewrite this as secant x times secant x plus tangent x over secant x plus tangent x dx. What did I do? Multiplied by the number 1. I wrote the number 1 in a bizarre way. Secant x plus tangent x over secant x plus tangent x. And the reason you do that is that happens to be the thing that works. And you'll see what I mean by it works in just a minute here. What should u be now? Well, we have a fraction. When we have a fraction, u is almost always the bottom. So I'm going to let u be the bottom. Secant x plus tangent x. So du is, what's the derivative of secant? Secant x tangent x. Plus, what's the derivative of tangent? Secant squared x dx. Notice in our fraction, in our integral, what do we have on top of our fraction? What's secant times secant? Secant squared. And what's secant times tangent? Secant tangent. So that's what I mean by it works. If you put that on bottom and let that be u, then you end up with exactly what you happen to have on top. So I don't know what clever person first figured that out. It wasn't me, but somebody came up with that nice trick. So this becomes the integral of 1 over u du. Works out perfectly. So we get natural log of secant x plus tangent x plus c. And I'm not going to run through it, but the cosecant one works exactly the same way. What do you think you multiply top and bottom by? Well, for secant, I multiplied by secant plus tangent. So for cosecant, I'm going to multiply by cosecant plus cotangent. The only difference is when I let u be cosecant plus cotangent, when I take the derivative, I get negative signs. The derivative of cosecant is negative cosecant cotangent. So when you do the u substitution, you get a minus. So you end up with minus ln cosecant plus cotangent. That's the only difference. I'm not going to work all through that. You can do that sometime if you're bored. Show that I'm not lying to you and it really works. Questions on that? Yes?
Why don't we just do the antiderivative for the secant? Why don't we just do it 1 over cosine?
And then what?
Could you use substitution?
All right, let's try that. So what you're saying is secant x, I could write it as 1 over cosine x, and then we would let u be cosine x, and then du would be negative sine x dx, and there's the problem. The problem is I don't have a sign anywhere, and I really can't do that sort of backward substitution thing that we've done, because I would have x equals arc cosine of u, and then I'd have to plug that in, and that sounds scary, doesn't it? I don't have any rules about arc cosines when I'm dealing with integrals. So unfortunately, that just doesn't work. Which is why we don't do it that way. It doesn't work out well. Other questions?